great to be here. Thank you for having me. I'm not really going to be talking about anything specifically related to Java tonight, so I hope that's okay. My colleague Olivia Petrie is also here. She's our community coordinator, and she is primarily responsible for our relationships with a lot of different meetups out there, as well as coordinating our own meetups and so forth. So, Olivia, thanks as always for being here. All right, so let's
indeed. Thank you, Olivia.
Let's look at advanced sharing options. No, I don't want that. I want to share the entire screen or the portion of a screen. Okay, I think we're getting closer to happiness. Hey.
Happiness has arrived. All right, folks, and then please feel free to drop in questions during the chat, but just recognize that Robert's going to handle them at the end. Thank you very much. Robert, it's all yours.
Thank you so much, Peter, and hello again, everyone. Can you see this slide in approximately a full screen?
You have full screen liftoff, my friend. Yes.
Awesome. That's great. Okay, well, thanks again. What I want to talk about tonight is a vector search capability in the Elasticsearch version 8, which is the newest release of the platform. As Peter mentioned, the housekeeping is tonight is this is conversational. Let's definitely have questions in the Zoom chat. I'll try to go through them at the end, or our parking lot, anything that that I don't know the answer to. I also definitely encourage you to take advantage of our discussion forum. The sum total of expertise of all of our elasticians and all of our users and so forth can be found there. So that's also a great place to learn more. Since there didn't seem to be a huge, I just want to make sure I level set a little bit here. Since Peter, it didn't look like there was an overwhelming amount of familiarity out there with the platform. Let me briefly.
Yeah, a little context setting is okay. Not harmful, certainly.
So Elastic is a data intelligence platform. You might know us as the Elk Stack. We, over the course of branding and companies and so forth, we're now thought of as Elasticsearch or the Elasticsearch platform. However you slice it, this is a stack that is used to create data intelligence applications. And the stack itself is what has traditionally been thought of Elasticsearch, Logstash, and Kibana. I prefer to think of it as a piece of the stack that goes out and does data collection, connection, and integration with various data sources. This is what's out there known as the beats, the file beat, metric beat, a whole set of beats that have been created by open source people, like maybe some of you. Beats, there's an open source spec. They're written in Golang, but there's many other different ways besides beats to get data into Elastic. You can use Logstash. You can simply use our bulk APIs. The whole thing is based on REST APIs. And then that layer feeds into the Elasticsearch itself, which is the engine that provides the relative search, scalable, high performance search, store, and analytics engine. This is great for structured and unstructured data. Just it lives as JSON documents. It's great for geo. It's great for text. It's great for anything that has any kind of structure or lack of structure that you want to get in there and perform high scalable relevant search applications. And on top of that, there's this visualization layer, which is Kibana. It's a very rich UI for both visualizing the data, developing custom dashboards, visualizations, analytics, and so forth, integrated into the stack. And on top of the stack, our company, we make a set of applications. Now, a lot of this is out there for free. That there's ways to use everything or almost everything we do for free. We we build applications that make data more useful to businesses around search, observability, and security. And then the platform itself is open and admits of thinking into the future. So one of the reasons why I really like talking to the open source community and people such as yourselves is the next great idea, the great use cases, the innovations are going to come from the people out there who are constantly banging on these kinds of platforms and thinking up cool new things to do with them. And then, of course, all this runs on top of an implementation, which could either be the cloud. Elastic runs on all the major cloud providers. You can run it in Kubernetes on premise. You can just run it on bare iron. Okay. So with that in mind, let's talk a little bit about our agenda. With that as a baseline, we're going to talk a little bit of and do an overview of what vector search is and why it matters. We're going to talk a little bit about how you compare vectors, what it means. You know, if you're going to search, you need some way of comparing data items to each other. So we're going to talk about vector similarity. We're going to talk about how to do vector search at scale. We're going to talk about how you can get your hands dirty, and then we'll discuss some additional resources and just do some general Q&A. So let's use the chat here. How many of you, what's the state of knowledge for the team out there around familiarity with vector search? Does vector search have meaning to you guys? Have you read up on it? So there's a 5. Thank you, Todd. There's another 5. Thanks, George. Thank you, Dan. I just want to make sure I'm, speaking at the right level here. And of course, I find myself very often speaking to audiences who knew a lot more about my subject than I do. So if that's the case, don't worry about it. That's certainly fine. Okay, thanks, Nikolai. So let's go ahead. It's nice to have a range of responses. So let's talk about what vector search is and why it matters. Well, when you think about the traditional ways of doing search, most of them are based on text matching. At the end of the day, all the improvements that you see over search is really just doing better ways of comparing text to each other. You know, even in the Elastic platform, when you think about analyzers, stemming, and filtering, you're still searching specific sets of letters that make up words and phrases. Okay. What vector search is, it just dispenses with this idea entirely, and it moves beyond text matching. It allows you to find a similarity based on things, not strings. What we mean by that is deeper notions of meaning and representations of content in the data. And it does this by encoding the data as numerical vectors with multiple dimensions that score the characteristics of data along these different dimensions as sets of numbers. And then the idea is you can apply mathematical comparisons to these vector representations, resulting in nuanced definitions of similarity that you can use for relevance ranking in search applications. And the vector encoding process is governed by deep learning techniques, okay? Neural networks, transformers, and so forth, basically the heart of the machine learning practice. But the good news is these techniques for doing these kinds of practices have become ever more democratized. You see them in Lucene 9, you see them in the Elastic platform. There's a wide variety of tools out there already for generating and training models. And with version 8 of the Elastic platform, the tools and techniques to create vector search-based applications are available to many, many people with just basic knowledge of the platform. So why do we want to do this? Well, computers aren't really very good at some things that humans just take for granted. So if we look at the pictures on the right here, we got a guy trying to get a cab. Call me a cab, and the woman's response is, okay, you're a cab. Well, that's probably not what he had in mind. But the thing here is conveying how important this context is to a computer and a search application is not easy. So how do we find a convenient way of gathering the context needed to really understand the meaning of this guy's request and performing an appropriate response. Another example is we have these two images, and we can tell that they're both of a rabbit. But the way that we can tell that there is some rabbitness inherent quality to these images is deceptively difficult to teach a computer. There's nothing at an obvious glance that relates them by color, by shape, and so forth. But teaching a computer that there's some similarity between these two images of a rabbit is deceptively difficult. And the ability to redefine similarity as the nearness of pieces of data in a vector space allows us to capture the relationships and context that would be very difficult or even impossible using traditional search techniques. And there are also some kinds of data sets that come up in cybersecurity and other disciplines that start out life as vector sets, and it's convenient to work with them as vectors in that case. So how does this work? Let's talk a little bit about the mechanics. Well, as we said, the way this works is that data is encoded into multidimensional vectors that are sets of numbers. And this is achieved using techniques such as neural networks and transformer-based models, which generate models of the data. And these machine learning techniques organize the vectors into searchable spaces. And the model ensures that vectors that represent similar items ought to appear near each other in the space. And we'll get into this concept of nearness more formally in a few slides. Now, there's many tools and techniques out there already that perform this kind of embedding modeling. For word embedding, there's things like Word2Vec and Glove. For language modeling, there's the BERT transformer model, which helps computers understand the meaning of ambiguous natural language by gathering information from the context. For images, there are a lot of convolutional neural network techniques to process, classify, and segment images into feature vectors. And for audio, you can do things like generate spectrograms, via fast Fourier transform, for example. The key point to remember about all these techniques is that not only do they vectorize the data, they also organize the data in ways such that the desired relationships between the data items are represented by the model. It allows the model to be used for things like data classification, future trends and prediction, clustering, and so forth. So let's talk through a really simple initial discussion here of the mechanics of this. So let's say we want to build an image search application that's incredibly simple. Well, we might pursue this by first building a model that classifies images. So we can imagine, for example, a dimension on which we're going to characterize images. And we'll call this dimension the realisticness or cartoonness of the image. And we can imagine feeding an image of this model and assigning the image a score, right? We're going to give it a number, we'll say something to the right of 0, some positive number means it's cartoonish, and something to the left of 0, meaning negative, maybe is something more realistic. So each image we model this way is assigned a score along this dimension. And we can add additional dimensions. So we might also want to describe the image based on the mammalness or birdness, let's say, of the image. And again, images processed into the model, giving a score along this axis as well. So now we have a two-dimensional vector space, sort of like a Cartesian graph. And this simple model allows us to classify images based on these two dimensions. And every image we feed into this model is given a position in the vector space. Again, this is drastically oversimplified. Typical vector dimensions for real applications are much larger, in the hundreds or even thousands of different dimensions. Okay. But this simple discussion serves to give you a flavor, right? Now, how do we use this? When we want to query the model, notice that we also vectorize the query. So we feed a query such as, what images are most similar to this elk, through the same model, and we come out with a vector. This is a query vector. And then we ask, which of our vectors in the vector space is most similar to this elk we're querying against? All right, so So feeding the elk through the model allows us to make sure we're comparing vectors to vectors, or apples to apples, or elks to elks in this case. And the thing about that, what is nice here is when we do this, we can see where the query vector lies in the space. And we can compare it with our indexed documents or images. And we get this nice list of results that we can rank by relevance. That's the key thing that you do with platforms like Elasticsearch. And using vector similarity is the way we can rank these results by relevance. And we'll talk about vector similarity in a couple more slides. Now, remember also, there is a trade-off here. When you're working with trying to build a real model that uses large numbers of dimensions, you have to trade off the amount of time and computer memory and CPU that it will take to do so. Now, it's also important to remember that the deep learning techniques people use to build these models, the dimensions of these models don't really have names like mammalness, birdness, or realistic cartoonness. These vector space dimensions are not interpretable by humans. They live inside a neural network, let's say, or a transformer model. And they live as nodes inside the network whose job it is to assign coefficients to nodes in the mathematical space. Now, how does a neural network know what these coefficients, these numbers are supposed to be? Well, the models are trained by humans, learning with a teacher. You feed in some models, you tweak the coefficients manually, and eventually the model learns, this deep neural network learns where to classify images based on what you've taught it. So at a certain point, it starts to generalize, and then it becomes useful for classifying images, finding image similarity, predictions, and so forth. It begins to be suitable for modeling a use case. And this opens up some really interesting ideas about what you can do with vector search. Well, probably the most well-developed set of use cases around natural language processing. Semantic search, question answering, and many others. And vector search makes it possible to create and deploy learning models of natural language alongside traditional search applications to provide richer search experiences, right? So for e-commerce, it's used for things like recommendation engines and personalization. As I mentioned, image search and audio search in multimedia recommendation systems. And then there are also, as I said, there are some use cases in cybersecurity where data occurs naturally as vectors, and you can use vector search to do predictions about attacks, infer the presence of viruses and so forth, and enabling cybersecurity to sort of be a little less reactive and more proactive in defending your network perimeter. Now, in order to use these ideas, we do have to have some well-defined ideas and notions of comparing vectors to each other, okay? So in the simple example above, we showed how our query vector was compared to the indexed vectors in our animal data set, and we ranked the results returned by how similar the index vectors were to the query vector. But that's, of course, going to depend on how you are comparing vectors to each other. So, you know, red and green, for example, are going to be nearest neighbors in this picture if we're measuring the endpoints of vectors, the distance to each other. But blue and red are going to be more similar if we're measuring angles. So the choice of a similarity measure is a fundamental choice when creating vector search applications. In fact, the people who build models and worry about inference and so forth, this is a fundamental decision they're going to make. And you can see that the importance of that choice is reflected in the fact that when you create an index in Elasticsearch to do vector search, the similarity metric is a fundamental choice in the description of the index. And we'll see an example of what that looks like as well. So in Elasticsearch 8, there are 3 different ways to measure vector similarity. Cosine similarity is probably the most common. It simply measures the angle between vectors. Now, very often you are not able to normalize vectors. You may have vectors of very different length that you're comparing together. So cosine is the most common because you can't always normalize vectors, right? You can't always normalize vectors down to the same length. You may have good reasons for wanting to keep different size vectors. For example, you may be comparing documents that are very different sizes, and you need to keep that information. So when you in this picture, when you're measuring via cosine, of course, blue and red are going to be most similar to each other. Now, if you want to use cosine similarity, but you're able to normalize all of your vectors, including the query vector, you should use a dot product measure, because it's an optimized, faster way of computing the cosine. And this can be thought of as a total quantity of effort in the same direction. And this metric can definitely capture popularity as well as occurrence count in vector search applications. Finally, if you're really interested in length comparisons, you can use Euclidean distance, or what is also called L2 norm. This just measures the distance between the endpoints of vectors. And under that measurement, the red and green would be the most similar vectors in this particular picture. And again, the choice of this is going to be based on your use case, the design of your model, the design of your application, and so forth. So as I said, the choice of similarity measure is so important. You can see here, when you create an Elasticsearch index for vector search, you have to specify the similarity measure as one of the key factors. You also want to include what we call a dense vector field, which is the data type that holds the vectorized information, the number of dimensions, and you're going to set index to true to let Elasticsearch know that it's going to have to build indices to do approximate nearest neighbor search, and we're going to talk about that. This is all in the documentation. I'm going to share those links with you later on. And by the way, the vast majority of what I'm showing and discussing with you here today is free and open. There may be some certainly if you wanted to use machine learning without a teacher, you would need a license. But I think everything else that I'm discussing is completely free and open. And there's a lab I'm going to show you that you can use with as long as you have like an 8.3 or 8.4 cluster, I think you're good to go. And if worst comes to worst, just fire up a trial. Well, you'll have like a 30-day key, but I think you're good to go for most of this, completely free and open. So let's talk about how to do this at scale. If you got a big index full of vectorized data, what are the mechanics here? What are the ways in which you're going to be able to search it? Well, back in 7.3, we introduced the dense vector type, where you could calculate the similarity of a query vector to every other vector in the data set and rank it by a script source. So this is brute force, right? And this is a brute force, a comparison of a query vector to every other vector in the data set. So unless you're working with very small indices, this is just not really going to scale. The time complexity is on the order of the size of the data set by the number of vector dimensions. And if you have real world size data, this probably isn't going to be what you need. So Elastic has embedded an approximate KNN search algorithm where you sacrifice a little accuracy for a really good guess of the K nearest neighbors. And it performs really well on large data sets. And this is the Hierarchical Navigable Small Worlds algorithm. This is very common. You see it in FACE, you see it in NMS Lib. A lot of the vector search platforms out there have arrived at using HNSW because it's got the accuracy and performance characteristics that people need. HNSW is native in Lucene 9, nurtured by Elastic. Again, we really think this is the right way to go for the platform. The way this works is it's a layered graph that represents a search space. And search it's great because Elasticsearch optimizes search speed by doing schema on write. We index on write. So we index using the search algorithm. That means when you've got a vector here, it comes in and it's established in a layer. And then another vector comes in, you use a similarity measure to figure out the distance to that vector. And then you might employ a little bit of randomness to decide if you're going to go to another layer. The idea is you instill a series of layers with the full data set at the bottom. And you search starting at the top where you have a very sparse set of vectors. But the idea is you're able to quickly close distance between the query vector and the vectors in your result set. And every time you run out of close nearest neighbors on a given layer, you drop down. Every layer down is going to have a larger set of candidates, and you compute where we are. It's a greedy search algorithm. So the greedy search algorithm says, I'm going to look around myself and find the best fit based on my similarity measure. I'm going to hop over, and when I run out of better choices, I'll drop down. When I drop down, I'm going to collect the k nearest neighbors. That's my result set. And because I know how far those guys are me using the similarity measure, I can rank the results by similarity. So we think, well, this is the horse we're riding. We think this is the right approach. We've made it native in the platform. We're nurturing it as native in Lucene 9. We really thought it was important to go native on this feature because we really wanted to be able to marry it to the rest of the platform. And as a result, we've got things like, filtering and aggregations and hybrid search with standard search techniques that fit seamlessly in with searching vectors. Okay, so that's why we have made this choice. Now, as I said, we could have done things like face, but we didn't want to not be native. NMS Live is C++, and we wanted to have a pure Java seamless solution baked into the Lucene platform. So here's what this looks like. Here's how it all fits together. Elastic works very much on a bring your own data and bring your own model perspective. Outside of Elastic, you perform your model development. You gather a bunch of data. You import models. We accept Hugging Face models, anything done with PyTorch, and then others like scikit-learn, VGBoost, LightGBM, and so forth. You can import these into Elastic, and in fact, there's a lab I'll show you how to get a hold of to show you how to do this. You ingest the corpus of data, and then you perform inference to vectorize the data. Maybe you end up with a reindexed set of data that incorporates an inference with the vectorized data as one of the fields of the index. And then you're ready to start searching. You have a similarity measure and HNSW. You can accept incoming queries that are then encoded by your model. And then you return results to the user ranked by the similarity measure. And of course, you can do this in the UI, but of course, the real beauty is our REST APIs make this easy to embed in applications. So here's what this looks like in 8.4, which is the newest release of the platform. You can tune this regime. There's a couple of key parameters here. The num candidates parameter is the number of approximate nearest neighbor candidates to consider on each shard in an index. Okay. The search computes the similarity of the candidate vectors to the query vector and selects the k most similar from each shard. At the end, the merge is done from each shard to return the global top. So each shard index contributes its top k, and then a global top k is extracted from that, and that's what's returned as the result of the query. Now you can tune this. If you increase the number of candidates, you will get a more accurate search because you'll have a higher probability of finding the true k top nearest neighbors at the cost of a little bit of a slower search. If you want to increase the performance of the search, you can decrease the number of candidates with potentially slightly less accurate results. And again, this is going to depend on you benchmarking, testing the application, and seeing how this works. But we felt it was important to give you the knobs and switches you might need to tune this best for your application. So in 8.4, brand new, you can filter in these queries as well. You can return the top k documents that also match a filter request. You can do hybrid retrieval. This is really cool. So you can find the top k equal 5 vector matches and combine them with the matches from a match query, and finally return the top scoring results, some number. And they're combined as if you did a Boolean OR between them. The top k vector results represent the global nearest neighbors across all index shards. And you can also do aggregations now. So you can compute aggregations, you know, your ags are computed over all the documents that match the search. For KNN, the ags are calculated on the top K nearest docs. If the search also includes a query, the ags are calculated on a combined set of the KNN and the query matches. So this work is ongoing. We're continuing to drive this into the platform. The 8.x release chain is going to feature continued improvements in indexing speed, and this is an open GitHub repo. So I'm going to later on, you guys will have a PDF of this talk, but we're really interested in feedback from the community on this regime and how we're doing it. So we really want to hear from you on this GitHub issue. There are a couple of free ways for you to get your hands dirty with this. If you guys have not used the Eland machine learning client, it's a Python client. It lets you just throw models into Elastic. I definitely recommend it. And once you get your arms on that guy, there's a blog that will walk you through a complete example of importing a natural language processing model, a bunch of data, producing the right inference pipeline with a couple of processor steps, doing a reindex, and then showing you how to do approximate nearest neighbor search hands-on in Elastic version 8. Okay, additional resources here, all the documentation you could ever want on the KNN API, on natural language, on our dense vectors. We've got blogs, we've got videos. And by the way, I don't know if you guys know this, we publish benchmarks regularly on the performance of the product because we want everyone out there to know that we produce what we think is a high quality, high performance product. So this is a public set of regularly produced benchmarks on how the product performs. And I encourage you to take a look. As I said, I'll make sure there's a PDF or version of this deck available to you guys, because I definitely hope you'll check all this stuff out. That's what I got. I want to say thank you. Thank you so much for the time. And I want to also say that we run a bunch of meetups. They're free. We serve refreshments. So you can check out the Elastic San Francisco user group. We have other user groups as well. We do meetups. We talk about all kinds of cool stuff. You can come see our cool new San Francisco office and have a glass of wine with me. And we would love that. And let me just say thank you again. I will stop the share and let's chat. Are there any questions?
Cool. Yeah, nothing in the chat at the moment, but folks, if you have any thoughts or questions, now is a good time to enter them in. Or since this is a smaller group, we can probably just go off mute and dialogue. So yeah, bring it, folks.
And you know what? If you don't have anything here and now, find me on LinkedIn. My email is firstname.lastname@elastic.co.
Just drop Robert. Just drop it into the Zoom chat.
Oh, sure.
I think we already have one question. Go ahead. Or not. Okay.
I have a question.
Yeah, I thought so. Okay, go ahead. Yeah, please.
Okay, so compared to the old vector space model from the old times, the similarity between vectors, I believe it's computed the same way, isn't it? It's just that probably the implementation is different because we used to have big vectors the size of the vocabulary of tens of thousands of, that was the length, and it would be implemented in a sparse way. While now you have a small dimensions, maybe 100, 200, and it's fully populated. But apart from that, the similarity is computed the same way. It's just the matching is done differently, isn't it?
Yes, I think that's essentially correct. And we found that using dense vectors allows us to be more computationally efficient, I believe. But yes, if the matching is done differently, it uses this approximate nearest neighbor search. The idea being that for large data sets, and the data sets out there are only getting bigger and bigger, we found that this HNSW approach yields pretty good results for large data sets.
Cool. Thank you.
Cool. Any other questions, folks? Yeah, feel free to just let me make sure that mute permissions are enabled. Yeah. You're welcome to go off mute and just chime in if you like, or if you prefer the chat, that works too.
I hope I didn't bore your audience, Peter.
All is well. I think you're getting some thank yous, and no, you're fine.
And I think I only said the word Java like once or twice in the whole presentation.
I think everybody knows Elastic is a mostly Java server, and so sure, there's clients in any language, and there's beats for all these different things, and ingest agents and yada yada yada. But I mean, I think we all know that Elasticsearch itself is a predominantly Java code base. So
what I hope to be able to do, and this is completely unofficial, all the beats that are out there, they were written in Go, which is, for my money, kind of a strange choice. Peter, you may know that the beats are sort of being subsumed to what we call the Elastic agent.
Exactly.
And there's an integration regime and plugin regime for Elastic agents. It doesn't exist yet, but eventually there's going to be an SDK for that agent. And I hope to be able to come back and talk, I imagine sometime next year, about writing a Java integration, a Java plugin for the Elastic agent.
Sure,
That's
yeah.
really cool.
Yeah. That sounds great. Yeah. I mean, I only worked at Elastic for about, a little shy of 2 years, but, I have to admit, ingest was one of the things I heard the most about. And it was, it was often good, but not always. So yeah, I know the agent thing has been going on for a while, and I think represents a nice cleanup and way forward that's going to make things a lot easier for Elasticsearch users. So I think that one's pretty exciting. Yeah.
Well, the other thing that I like, and and this is again free and open, is gobbling up files. There's a PDF file. There's a file system watcher now. It'll just watch for PDF files and other things like that. Grab them and throw them into indexes.
Cool.
Oh, very cool.
All right, folks.
Well, I have another question.
Yeah, please go right ahead.
I'm not familiar with the latest versions of either Elastic or Lucene. Since Lucene 6, I haven't kept up. But I'm curious, do we have to provide our own embeddings or transformation into embeddings? Or can we just send the documents as text, and Elasticsearch or Lucene is smart enough to say, okay, let me apply some deep learning and convert them into embeddings?
You need to provide a model. Okay. You need to provide a model off of Hugging Face, off of PyTorch, something like that. You need to provide a model. Now, the exception to that is if you buy a license and you feed in a bunch of data. Elastic has a paid feature for machine learning. It'll essentially build a model for you. It'll inspect the data. That's a paid feature. But for free, if you have your own model out there with PyTorch or Hugging Face, whatever, you import it into Elasticsearch, and then it will translate. It will perform inference on your data and vectorize.